Chapter 3, Lecture 1, Steady State Conduction. So our lecture objective for this series of lectures is to understand the concept of thermal resistance and develop thermal resistance network for practical heat conduction problems, solve steady state problems that involve multi-layer, rectangular, cylindrical, or spherical geometries, develop an intuitive understanding of thermal contact resistance and the circumstances under which it might be significant, analyze fin surfaces and assess how efficiently and effectively fins enhance heat transfer, and finally to solve multidimensional practical heat conduction problems using conduction shape factors. So let's begin with defining exactly what we mean by conduction. So in conduction, you have, as an example, this rectangular wall, and you have temperature on one side of the wall, and that temperature is being conducted atom by atom through the interior of the wall to the other side of the wall. So here we can write down Fourier's law of heat conduction. Q dot equals minus Ka dt over dx. We take the dx to multiply through by dx and integrate from on x from x equals 0 to x equals L. So here this is a one-dimensional problem, so we're just integrating along x. The t is going to be from t equals t1 at the left side of the wall to t equals t2 at the right side of the wall. So when you integrate this, k and a are constants. So these come outside the integral. And so this integral is fairly simple to do. You end up with this equation here. Q dot equals Ka delta T over L. So this is basically shows that the heat conduction through a wall is a straight line under steady state conditions. It's proportional to the average thermal conductivity K, the wall area, and the temperature difference, and it's inversely proportional to the wall thickness. So this equation may look kind of familiar to you. If not, we can certainly rewrite it so it is a more familiar looking term. If you take a look at current flow, you have the typical Ohm's law, I equals delta V over R. This is sort of what this equation looks like. If you look at this, could be delta T over some constant, where the constant is L over Ka. So we define L over Ka as the conduction resistance of the wall. So this form of our equation we developed in the previous slide is exactly like Ohm's law. So here we can sort of imagine a exact analogy between electrical current flow and heat flow. In current flow, you have a current element, resistor, and you have a potential difference between either sides of the resistor. So here, the current flow is going to be the difference in potential, V2 minus V1, divided by the resistance of the wire. This is exactly the same situation we have for heat flow, except in this case, what's driving the flow of heat is the delta temperature. And R plays a similar role. It's not the resistance, however. It is what we've defined as the resistance of the wall. So exactly the same analogies we use for series and parallel currents when we studied university physics applies to this scenario as well for steady state heat conduction. So now that the temperature has reached the outside of the wall, it is now convected away from the wall by Newton's law of cooling. Q dot equals H times the area times the temperature difference between the surface and infinity, far away from the wall. T infinity is the temperature farther away from the wall. But again, this equation we can rewrite in terms that makes it look like Ohm's law. The numerator is the delta T, and the denominator is resistance we define as the convection resistance of the surface. It's given by 1 over H times A, area of the surface. So again, we've effectively replaced our heat conduction problem to something we know, a simple electrical network, where the temperature is driving the flow of heat away from the wall, and it forms the same formula as Ohm's law. So now, having developed the idea of electrical resistance networks and how they can apply to steady state heat conduction in plane walls, let's look at a simple case where we have steady state one-dimensional heat transfer through a plane wall of thickness L, area A, and the wall has a thermal conductivity K. Let's imagine there's fluids on both sides. So on this side, well away from the wall, the fluid is at T infinity 1. And on the right-hand side, well away from the wall, the fluid is at temperature T infinity 2. So using our relationship we developed, Q dot equals delta T over the resistance of the wall. In this case, we're going to treat the thermal conductivity resistance as a total. And so since these are three resistors in parallel, or three equivalent resistors in parallel. So on this side we have, let me draw a picture here. On this side we have a resistor on this side. We get it to a wall. We have a resistor on the wall, and on this side we have another resistor. So this resistor is the resistor for the convection in fluid 1. This resistor is the R of the wall. And finally, the final resistor on the right is the convection resistor for the fluid 2. So this is very simple to just add these numbers up and apply this equation. So we can directly extend this if we have two walls hooked together and fluids on each side of the walls. So again, now all we do is simply add another R value for the wall 2. So now we have R convection 1, R wall 1, R wall 2, and R convection 2. And those just add like resistors in series. Add like resistors in series. So let's take a look at a practical example. Here we have a wall that's 5 meters wide, 3 meters high, 0.3 meters thick. One side of the wall is 16 degrees C. The other side of the wall is 2 degrees C. We want to determine the heat loss of this particular wall with those conditions. So here we can use our thermal conductivity equation, K sub A delta T over L. So we're given what K is, we're given what A is, delta T, we're told what the temperature differences T1 and T2 are, and the wall thickness is 0.3. So we calculate and we get 630 watts. But we can also calculate this using our electrical conductivity equivalent. Q dot is delta T wall over the resistance of the wall. Here we can first calculate the resistance of the wall, which is L over K times A. We get 0.222 degrees Celsius per watt. Then we apply our equation, 16 minus 2 over the resistance value, 630 watts. So again, in this kind of trivial example, the first approach would be sufficient, but when you get multiple walls connected together, it's actually easier to do the resistance equivalent network. So let's take a look at a more challenging example, example 3.2. Here we're going to examine the heat loss through a single window pane. So here we have a window pane that's 0.8 meters high and 1.5 meters wide. It's a thickness of 8 millimeters. So the thickness of the window pane itself is 8 millimeters. It's a thermal conductivity of 0.78 watt meter Kelvin. We're going to determine the steady state heat transfer through this glass window and the temperature of its inner surface for a day which the room is maintained at 20 degrees C. So this is the inside of the house. Far away from the window, it's 20 degrees C. While the temperatures of the outdoor is minus 10 degrees C. We want to take the heat transfer coefficients on the inner and outer surfaces of the window to be H1 and H2 respectively. This also includes the effect of radiation. So here, what we're told is we know the thermal conductivity, we know the area of the wall, we can find this 0.8 times 1.5. So we can calculate the individual resistances values. So for example, Ri, which is the resistance of the inside, uh, is 1 over H1 times A. The R of the glass, L over Ka. And the R of the outer surface is 1 over H2 times A. So we can calculate those resistance values. And since these are in series, we can add those resistances. So the total resistance is the sum of the individual resistances. And finally, the rate of heat transfer is the delta T over the total resistance. So this is the T infinity 1 inside the house. This is the temperature outside. So we get 266 watts. So knowing this rate of heat transfer, we can sort of go backwards and we can calculate the individual temperatures. On the inner surface, we have Q dot is T infinity 1 minus T1 over R convection 1. So that says T1 is equal to T infinity 1 minus Q dot R convection 1. This value is given, about 20 degrees C. Q dot we calculated, and R conversion 1 we calculated as well. That's the 0.08333 value. So the temperature on the inner surface of the glass window is minus 2.2 degrees C. So example 3.3 extends to example 2.2 by adding another window pane. So this is a double pane window. So it has the same height and same width, but now we add another layer of glass. And so here we have a 4 millimeter layer of glass, a 4 millimeter layer of glass, and a 10 millimeter layer of air sandwiched between the two pieces of glass. We still have the same temperatures. On the outside it's minus 10 degrees C, and on the inside it's 20 degrees C. So we can look at this as just adding a couple more resistors in our network. We can calculate Ri, which is the same as before, R1, R2, and RO for the outside. So since all these resistances are in series, we can add them up like resistors in series. We get a total resistance value of 0.4322 degrees C per watt. We can find our steady state heat transfer, delta T over R total, just like before. The only thing that changed is our total resistance value. So we get 69.2 watts. So we can repeat the calculation for the inner surface of the temperature of the wall, and we get 14.2 degrees C. So this is a lot higher than the single pane window, and this is why it's preferred to have double pane windows in your home. So I'll see you in the next lecture.